Okay, now we're going to take planetary circulations you've looked at, and we're going to draw them down to the weather systems we get. We live in the mid latitudes, so let's talk about our weather, what controls it. So, there are a lot of things that go into our weather. We've already discussed all the different aspects of different things that work to shape it. So, let's start with just air masses. There are a lot of source regions for air masses, and there are several different types. We can have an Arctic air mass that forms up over nearly near the North Pole, even into Siberia. Extremely cold. We had one come down this last winter. Uh, we can have continental polar air masses that form mainly over Canada. We can have continental tropical air masses which form over the desert southwest of the U.S. Maybe a maritime tropical air mass. We have them off the west coast of the U.S. or off of Mexico and off the southeast coast of the U.S., even in the Gulf of Mexico. And there are maritime polar air masses, which form basically over the cold ocean waters. So each one of those air masses is separated from another air mass by a front. And that is the key here. There's a boundary between the two air masses. So that is what controls the weather. When you're in the middle of one of these air masses, you're probably going to have fairly decent sunny weather. It's along that boundary that the bad weather occurs. So air masses have uniform temperatures and have uniform moistures to them, and they don't really change if you go across a lot of distance within them. So, but when they get to the edge of them, that's where the real sharp changes go. Maritime tropical air masses do not modify as much as polar air masses. Why is that? Well, they form over warm ocean water or warm, and when they're coming northward, it takes some time for that warm water to warm the land to undergo significant modifications. Whereas if you bring in something coming off of pure ice on the north to the north and then bringing it over the oceans or over land, it's going to modify pretty quickly. So where these air masses meet are fronts. If that front's not moving, and it does happen from time to time, we had one the other week that caused tremendous rainfall through the Midwest along the Ohio River into West Virginia. That front didn't move for several days, so we had a series of low pressures move along it. And these lows, we're going to talk about them, but right now we'll just deal with fronts. Notice the warm air is always rising up and over the cold air. So more of the cloudiness is always going to be on the cold side typically. On a warm front, you can see the same thing, except the warm front's advancing. How do you know it's a warm front? Well, if it at your house and it moves past you, did the temperature go up? And probably the moisture went up. If that happens, then it's a warm front. If it got colder, then it's a cold front. That's the simple difference. Cold fronts, remember cold air is denser. So when cold fronts are moving or advancing, they're very steep. They tend to rise up much faster into the atmosphere. So they're going to push the air up faster, so you tend to get more thunderstorms right along a cold front than along a warm front. And fronts can move down south in different directions. There is something we call a backdoor front on the East Coast. You actually get some out in the Rocky Mountains or along there as well, where the front actually comes out of the north or even northeast and it backs into the area. When they come in down in my neck of the woods into Virginia, they'll have come off the Atlantic Ocean, a lot of the air, so you might get really low stratus, fog with them. It can get kind of miserable for several days. And the spring is a very high time to get these in the East Coast. So they can actually ruin a whole week of what would otherwise be a very good weather week. Occluded fronts, on the other hand, they typically form late in the cyclone's life cycle. Basically, the cold air that's been moving eastward passes and catches up to the warm front and pushes the warm air aloft, so you wind up with basically cold air on both sides of the front. One may be just a touch colder than the other, but the warm air is aloft. And you can see that here with this. So An extratropical cyclone is your typical low pressure system that passes your house. In the United States, we probably have 2 or 3 going on any given day across the country. So, with that in mind, don't look at it as having developed from a tropical system. Many times you hear oh, that was a really strong extratropical storm that came from a tropical system. But extratropical systems form all the time. They're always on the move across the country, and you've had several pass your house in the last several weeks. A matter of fact, you'll probably have one pushing a cold front through right now. So don't mistake the two. Extratropical cyclones form through a temperature contrast. There's cold air to the west and warm air to the east. When they initially form, they're fairly weak. Look on the A picture here on the Norwegian cycle. Just a weak low pressure system, not a real strong temperature gradient. As that low develops, it's pushing more and more cold air down in the west and warm air up in the east. So what you wind up is getting a tighter and tighter temperature gradient, and you start getting like a comma head to the cloud pattern. And eventually, even more cold air is arising. Now you're starting to get a little bit of an occluded front because the cold front is overtaking it. And eventually, you get a really nice circle, nice comma head, and a strong occluded front and a warm front, and here, a cold front here. And at about now is a lot of times when you get a triple point low. The triple point is right here where the cold front, the warm front, and the occluded front all meet. And many times you can get a new low pressure system form. They frequently may occur along the East Coast, but you can get them in the Midwest as well, where a big strong low goes up the Midwest and a new triple point low may develop. Maybe it's along the Appalachians, maybe over the Carolinas. So you can see here the incipient, you have a lot of divergence aloft. And that is the key. None of these lows form without divergence aloft. So you got to start that first. The more divergence aloft that develops, it helps the lower level systems to pull air in. If the convergence gets the air rising and begins to develop your low pressure. As that comma head develops, you're getting a stronger trough aloft. You're getting more intense divergence at that time and continuing until it occludes. You may get a dry slot that's coming in on the southwestern part as the front begins to occlude. Think about it. The cold air is coming down and it's sinking as it's moving on the west side into that dry area there along behind the cold front. So it actually can cut off the precipitation fairly quickly. One of the things I want you to notice is almost like a V shape moving up into that area where the dry air is coming in. And that is a key sometimes at cutting off precipitation much quicker than maybe the forecast had. And here is where it shows the triple point. All right, conveyor belt. Let's keep it as simple. It's basically looking at air masses. So you have a dry, cold air mass from the north coming in behind this low. What happens is that dry air mass is pulled into the system, but it sinks down on the west side of that low as it's being pulled in. It's cold air, it's sinking. So what happens is when it's pulled down at first, it's drying it out, and that's causing your dry, where your dry slot is. Now you have a cold conveyor coming off the cold water sometimes as well, and that's just the opposite. It actually lifts up into the storm, and it's coming off the water, so it has moisture with it. And then you have the real massive amount of moisture that comes with the warm conveyor belt out of the south, and that's where your heaviest rains may occur when it's overriding that cold layer. And you can just see these cyclone weather depending on what section you're in of the front. If you're to the north of the low, you typically may have more snow. If you're to the east of the low, more rain. If you're along the cold front, more thunderstorms. And you can see all the various low tracks here. They come from everywhere. But think about it. If they're coming out, the further south they're coming out and moving up towards your area in Ohio, the better chance they have to pull moisture in, maybe off the Gulf of Mexico or even off the east coast of the United States. And some moisture actually develops out here in the southern Pacific. So with winter storms, if I told you a low was going to move over Columbus and you lived west of Columbus, you would have a pretty good chance of getting snow in the wintertime if it was cold. Now, if I told you that same low instead was going over Toledo, all of a sudden a lot of Ohio is going to be in the warm sector. It might start out as a little bit of light snow or freezing rain, but it's probably going to shift over to rain, maybe even some thunderstorms. So just moving the low from Columbus to Toledo caused a significant shift in the type of precipitation you're going to get. And again, we know that temperatures in the cold core system, the air is very dense, so the pressure is going to fall faster. So what you find is a low aloft, a low at the surface, but the most intense low is further up in the atmosphere. And even when they tilt more, but they're non-occluded, but they're still there. It's still the coldest and the lowest pressure are aloft in the atmosphere. Warm cores are different. They're pretty stationary. There are no fronts around them. And a warm core actually changes from, think about it, it's heating the surface, the air is expanding, and as it's rising up, because it's warm, pressures are not changing as fast, so you actually wind up with an anticyclone aloft. And this is actually what happens in hurricanes. You many times will wind up with high pressure over top of a hurricane. So there are cold core anticyclones like polar fronts, warm core ones, but there are different mountain and valley breezes. Think about it with the mountains. If the bare walls get cold at night, they're going to flow down the slope. If they heat up during the day, they're going to flow up the slope. And you wind up getting cold air sinking. Chinook winds happen along a major mountain range. Basically, the Rockies are a great example of this. They take air that's been pushed up them and drop it down, descending. So say you had a strong east winds into the Rockies, and then it went on the other side of the Rockies and it got over the top. It's cold, it's dense, it's dropping fast down the west side. It's warming as it descends, and that is a Chinook wind. They can occur on the east side as well. They are known as snow eaters because they will wipe out a snowpack in minutes. And they can also, when you've ever heard of the Santa Ana winds in California, that's a Chinook wind, where it's come down out of the mountains, warmed up because of gravity pulling it down. And as it's warming, it's drying. Adiabatic compression takes place. It's basically a hot, dry wind. Hababs are just dust storms generated by strong thunderstorms. We get them actually down in Phoenix, in parts of Arizona, New Mexico. You can actually see them, and it's really interesting because sometimes you get the dust mixed in with the rain. It's just mud yuck. Heat bursts are a thunderstorm where the rain never reaches the ground. The air keeps warming because it's being pushed down by the strong convection. And as it's warming, it can raise a temperature from the 70s to 80s to over 100 degrees in a matter of minutes when these go by. But it doesn't rain at your house. There may be a lot of wind. So this is just beginning to look at our weather here in the mid-latitudes. So I just wanted to show you there's a storm developing in the Midwest. Here is 70-hour forecast. Here's low pressure, 1,000 millibars, basically over the corner of New Mexico and Colorado. Moisture feed coming in off the Gulf of Mexico and up here. Oh yeah, look here, there's a cold front right here. Thunderstorms along that cold front. This is an occluded low, so it's well back here. So you probably have a nice warm front out here. Here's all the rain area north of the warm front. So you can actually see with this low all the factors that we just discussed with the Norwegian cyclone model and with the conveyor belt model. They're all right here in this one little low. And with the wind coming into the mountain, you enhance the rising motion, you get heavier precipitation. That's why the front range of the mountains is going to get tremendous snowfall out of this. If you looked at it aloft at exactly the same time here, which should come up in a minute, what you see is a very, very intense cold upper level system. Gee, it worked. We said it should get colder. It did. And we have very strong divergence out in the left front quadrant of this low, right in here. A little bit out ahead of where the actual low is, but it's a occluded low, so it's back a little bit behind it. But all this divergence is what helped to form it. Now, we talk about high pressures, and I thought I would mention that. There is convergence occurring aloft back here. And what do you see aloft back there? At 1040 millibar high pressure. So that you can see how that related as well. So this is just an example what's happening in the today's weather, applying what all this long chapter has been talking about. So hope you got something out of that.